Let's unravel a scientific mystery that you've definitely faced on a hot summer's day. It all starts with something delicious and usually ends with a very sticky situation.
Oh, yeah, we've all been there, right? You're in a race against the sun, trying to finish your ice lolly before it just gives up and becomes a liquid disaster. But what is actually happening when that solid treat melts? Well, you're witnessing a pretty fascinating scientific process.
That whole process, it's called a change of state. It's really just your lolly moving from one physical form, a solid, to another, a liquid. And this kind of thing is happening all around us all the time. So let's break down the 4 key changes you need to know.
To really get a grip on this, we need to talk about 4 key terms. The best way to think about them is as 2 pairs of opposites. And they're all driven by one crucial ingredient, energy, which is usually in the form of heat.
Okay, first up, melting and freezing. When you add energy, heat, to a solid like ice, it melts into a liquid. That's your lolly puddle. Now, the reverse of that is freezing. Take that energy away by cooling the liquid down, and it turns right back into a solid. See? It's a perfect two-way street.
And our second pair is evaporating and condensing. If you add more heat to a liquid, it'll evaporate and turn into a gas. Just think of a boiling kettle. And just like before, it works in reverse. Cool that gas down, and it condenses back into a liquid. You actually see this every single time a window fogs up on a cold day. But to really understand what's going on here, we have to zoom in. I mean, way, way in, down to the microscopic level. You see, this is all a story about particles. So inside your solid ice lolly, the particles aren't just sitting still. Nope, they're actually buzzing with energy, constantly vibrating. But here's the key part. They are locked into fixed positions by really strong bonds. You can imagine it like a perfectly organized, but kind of jittery army of particles. So what happens when we introduce a new player to the game? Let's add some energy, say heat from the sun. This is where things get really interesting for our little particle army. That extra energy makes the particles vibrate more and more, until they get so wild they literally break free from their fixed spots. Those bonds weaken, and now the particles can just slide right past one another. The rigid structure is gone, and just like that, you've got a liquid. But hey, why stop there? Let's crank up the heat even more. If we keep pumping in energy, we can push those particles toward an even more dramatic transformation. With enough energy, the particles are moving so fast they completely overcome any of the forces trying to hold them together. They just escape and fly off in all directions, moving freely and totally randomly. Now you've got a gas. Our organized little army has turned into a chaotic, super energetic crowd. So we've seen the particle story, but how can we visualize this whole journey from solid to gas? Well, scientists use something called a heating curve, which is basically a map of what happens to the temperature as we add more and more energy. It's like a visual diary of a substance changing state. Let's take a look at a classic heating curve for water. On the side, we've got temperature, and along the bottom, we've got the energy we're adding. This thing tells a really fascinating story. Let's walk through it. Okay, in this first section, where the line is rising, we've got solid ice. As we add heat, its temperature climbs up and up. The particles are just vibrating more intensely in their spots. But then, look at that! The line goes totally flat. Something strange is happening here. We've just hit the melting point. For water, that magic number is 0 degrees Celsius. This is a critical threshold, the exact point where the state starts to change. Now look closely at this flat part of the graph. We're still adding heat, right? But the temperature isn't going up at all. So why is that? It's because all of that energy is being used for one single job, breaking the bonds that hold the particles together. The energy is fueling the change of state itself, not a change in temperature. So once all the ice has melted into liquid water, the temperature starts to climb again, until we hit the next critical threshold, the boiling point. And for water, we all know that one, it's 100 degrees Celsius. And there it is again, another perfectly flat line. Just like with melting, the temperature holds steady at 100 degrees. Why? Because now all the energy is being used to give those particles the final kick they need to escape and become a gas. So if there's one thing to remember, it's this. During a change of state, the temperature stays constant. Okay, so this process is fundamental, right? But it's super important to remember that these magic numbers, the melting and boiling points, they're unique for every single substance out there.
And wow, the differences can be huge. Water melts at 0 and boils at 100, but what about regular table salt? It won't even start to melt until you hit a scorching 801 degrees Celsius. And you need almost 1500 degrees to boil it. It all comes down to how strong those bonds are between the particles.
And just when you think you have all the rules figured out, science throws a cool curveball: sublimation. Some substances, like dry ice, don't even bother with the liquid phase. They go straight from being a solid to a gas. It's pretty cool, and it makes all that awesome smoke.
So, from melting ice lollies to boiling a kettle for tea, these changes of state are just a fundamental part of our world. And when you understand the rules, it can reveal some really surprising things about the environment around us. Check out this wild fact. On top of Mount Everest, water doesn't boil at 100 degrees Celsius. It actually boils at around 70 degrees. And the reason for that is that the lower air pressure up there makes it way easier for the water particles to escape. And that leaves us with a final little puzzle for you. If you're trying to cook pasta on Mount Everest and the water is only 70 degrees instead of 100, what do you think that does to your cooking time? Does it cook faster or does it cook slower? It's a perfect example of how this science has real-world consequences. Something to think about next time you boil a kettle. Thanks for digging into this with me.